All right, so now we're going to talk about the real important part of the fundamental theorem of calculus, which is part two. Hopefully you've looked at my video for part one. If you haven't, make sure you go back and look at part one of the fundamental theorem of calculus, because it won't make sense unless you've gone through that first. But so here's what it is. This is a kind of a little bit of a derivation. Part one, I usually don't ever see that asked as a question on a quiz or a test, but there's a lot of times I've seen this asked on a quiz or a test, basically deriving this formula, part two, for the fundamental theorem of calculus. So it's worth going through. Okay, so part one, what we figured out was that the derivative of the definite integral from a to x of some function of t dt is just f of x, right? It's just this function evaluated at your upper limit. So if that's true, if the derivative of this is f of x, then what would just the integral be? Well, that would have to be the antiderivative, right? The derivative of this integral is f of x, so to find just the integral, we would take the antiderivative of both sides. Now, recall earlier on, we were the common notation for the antiderivative of little f of x is capital F of x. Okay, that means the antiderivative of little f of x. And we know there should be a plus constant here, right? Plus a c there. Okay, so now let's take this equation and let's substitute x equals, that is an a, believe it or not, that's an a. If I let x be a, then this integral becomes the integral from a to a of f of t, and I have to plug in a there as well, right? That's x equals capital F of a plus c. Well, the integral from a to a, that's one of your integral properties. You're not moving anywhere, right? That's going to come out to be 0. So 0 is equal to f of a plus c. That means our constant is always going to be the negative of f of a, the negative of your antiderivative function evaluated at a. Now let's plug in x equals b into this equation, and we have the integral from a to b of f of t dt will equal capital F of b, I have to plug in the b there as well, plus my constant of integration, which we know is always going to be negative f of a. So if I put that in, this is our big result. The antiderivative, the integral, of a function from t equals a to t equals b of some function f of t dt is going to equal, remember, f means the antiderivative of your function. Capital F is the antiderivative of f of t evaluated at b minus your antiderivative of your function evaluated at a. And this is part two. This is huge because before, to evaluate a definite integral, we were using Riemann sums, and we had to take the limiting Riemann sum to find the exact area under the curve. This is going to give us a way to evaluate definite integrals by simply finding the antiderivative of our function and evaluating it at our two endpoints for our integral. Okay, so we're going to be using this for the rest of the quarter. A lot of times we won't even say it's the fundamental theorem of calculus part two, because it's just going to become natural for us. We're going to be doing it every single time to evaluate a definite integral. So, quick example. We could do a Riemann sum and try to find the area under 2x plus 1 from x equals 2 to x equals 5. Using the fundamental theorem of calculus part 2, we first find the antiderivative of this function, which would be x squared plus x. We don't need to put a plus c on there. Okay, this fundamental theorem doesn't have a plus c. What ends up happening if you put a plus c and you plug in the top number and the bottom number, the c ends up canceling anyhow, so you don't need it. So this is what's meant as capital F of x, x squared plus x. We now need to evaluate that at b and subtract what we get when x is a. So you've probably seen this in 21a. That's an evaluation symbol. It means we're going to evaluate it from b equals 5 to a equals 2. plug in 5 for both of your x's, minus what you get when you plug in the 2, and we get a final answer of 30 minus 6, which is 24. If you don't appreciate how much easier that was, you might try going back and trying to evaluate that integral using a Riemann sum. You will see it's much more work. In this section then, there's now a bunch of examples of just evaluating definite integrals. We don't need to use the Riemann sum anymore. So say I want to find the integral from 0 to pi of sine of x dx, which, because the graph of sine of x from 0 to pi is entirely above the x-axis, this could be interpreted as the area between sine of x and the x-axis. This would have been hard using our Riemann sum. I don't think we could have done it because if you recall, we were dependent on certain formulas like the sum of the first n counting numbers or the sum of the first squares of the counting numbers. And we don't have any formulas that add up sine of the first whatever numbers, right? So this would have been difficult, if not impossible. Fundamental theorem of calculus says first find your antiderivative, negative cosine of x, and we'll evaluate it from pi to 0. Pi goes in first, minus, don't forget the minus there, so it's minus negative cosine of 0. Cosine of pi is negative 1, so we get 1 plus 1. This area is 2. Now, what's going to limit us in terms of our ability to evaluate definite integrals is our ability to find antiderivatives. So we will spend some time in the next few classes working on how to evaluate certain types of definite integrals, finding antiderivatives more specifically. Okay, so I selected a few from this section that I thought might give you trouble and just want to show you how to do these. Okay, 1 plus root x over root x, I want to find the integral of that from 1 to 4. One of the things for antiderivatives we have mentioned earlier is if you have one term in the bottom, splitting it up into 2 separate fractions, 1 over root x and then root x over root x is a good technique. Then all I have to do is rewrite this as x to the 1/2. That's just 1. Find my antiderivative. Remember, you add 1 to that power and then divide by the same thing. So dividing by 1/2 is the same thing as multiplying by 2. The antiderivative of 1 is x. Plug in 4 for both of those, minus what you get when you plug in 1. I got an answer of 5. One more. There's some trig integrals in this section. And so if I want to find the definite integral from 0 to pi over 3 of secant x plus tangent of x, the whole thing squared. Good technique for finding antiderivatives. If you don't see it right away, rewrite this. And by rewriting in this case, I'm going to just FOIL this out. I'm going to multiply it out. And so we get secant squared x plus 2 secant x tan x. Those would be your 2 middle terms, plus tan squared x. One of our properties is if you want, you can split this up into 3 separate integrals. I chose not to, but you will need to use an identity for tangent squared of x. That's secant squared x minus 1. Then I combine these 2 secants squareds and just integrate each one separately. Your antiderivative of secant squared is tan x, so I have 2 tan x. This is secant's derivative, so this would integrate to 2 secant of x minus x. Evaluate from pi over 3 to 0. Plug in your pi over 3, plug in your 0. It comes down to trig if you want to get the final answer that most books would have. At the very least, if you're rusty on your trig, if you would even just stopped right here at this step, you should get most of your credit because this is the right answer. It's just, you may recall, the tangent of pi over 3 can be worked out with a special triangle. That's root 3. Same thing with secant of pi over 3. So this could be simplified to something a little bit nicer. All right. That's the fundamental theorem of calculus, part 2.